Hi everyone. In this video, we're going to go through a couple of the Hardy-Weinberg expectations and see where they come from. So we're going to start out by looking at the parental generation, right? The P generation. So we're going to follow a couple of totally made up alleles. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. All right, so that we got 14 of these alleles. And then let's just get another color. So we've got a blue. Maybe we make a red allele. So let's do 1, 2, 3, 4, 5, 6. Okay, so now we have 6 red alleles and 14 blue alleles. So our gene pool is made up of 20 total alleles. And in that gene pool, we have 10 individuals. And that's our population. All right, so we have a population of 10 individuals, and in that population, these are diploid sexual organisms. So we now have 20 alleles in that population. So when a gamete comes from that population, one of two things, there are two possibilities for that gamete. Remember that the gametes in this case are going to be haploid. And so we've got gametes coming over, and we can do expectations using a Punnett square. So what we're going to do is make a Punnett square, and we're going to look at how likely it is the first allele is going to be red or blue. So let's start out with blue. So we've got those individuals, and there's a 70% chance. So we always work in proportions here, and you should make sure that you're always using either the proportion or percent, whatever's being asked for in the question that you're dealing with. So there's a 70% chance, and as a proportion that's 0.7, of getting a blue allele on the first draw from that population. So we're making a random gamete, and that's our first chance. There's a 30% chance that we get a red allele. And of course, those two add up together to a 100% chance. So we get 1. All right, so if we add those together, we should get 1. We should always get a 100% chance. And you can kind of do a quick check on that to make sure that you understand it by basically asking whether or not they add up to 100%. So that's true on our first attempt, on our first gamete that we produce from this population. So there's a 70% chance that that gamete is drawn first, that the blue gamete is drawn, or the blue allele is drawn first, and there's a 30% chance that the red allele is drawn first. All right. So that's the same for the second gamete as well. 0.3. And we'll have a look here. 0.7. All right. So to combine probabilities, the way that we do that is we multiply those probabilities together. So to get the chance that we draw first one blue allele and then a second one when those gametes fuse to make our zygote, that's 0.7 multiplied by 0.7. And what do we get? A 49% chance that we're going to get 2 blue alleles in that zygote that's formed from this gamete and this gamete together. So the probability that we're going to get a red allele followed by a blue allele is 21%. And the probability that we're going to get a blue allele followed by a red allele is another 21%. So I'm drawing these intentionally in different colors so that you can kind of trace some of this as we go through. So these together are our heterozygotes. For the most part, it doesn't really matter which one comes first versus which one comes second. Right? So we're always going to get, when we're looking for the total heterozygotes in that population, we can add those together and we get 0.42. So we're adding those together, 0.21, 0.21. That's 42, 0.42 or 42% heterozygotes. And I'll just abbreviate that heterozy. So 42% chance that we're going to get a heterozygote in that population. Then we multiply 0.3 times 0.3. Well, 3 times 3 is 9, but these are proportions. These are less than 1. So when we multiply those together, we wind up getting 0.09. So we can now take all this and move it over, and we can kind of do a check. So the Hardy-Weinberg equation itself, is p squared plus 2p times q plus q squared. Okay, so what does that mean? Well, when we do that, p times q, so p, if you remember, is the proportion of the dominant allele, or whatever our first allele is, and q is the proportion of our other allele. So we can now plug that in, 0.7 and 0.3 for each allele. So in this case, squared is just multiplying it by itself, so 0.7 squared, so 0.7 times 0.7, and guess what? That's 0.49, just like we calculated a minute ago. So the next thing that we need to calculate is 2pq. So the reason we're doing 2pq is because there's a 30 times 70% or 21% chance that we're going to get a heterozygote that has a red allele first, and there's another 21%, 0.7 times 0.3, of getting a heterozygote that has a blue allele first. So that together gives us a 0.42. So 2 times 0.3 times 0.7, and that winds up giving us 0. Whoa, that's a big 0. Some days. 0.42. And then we're just left with the homozygotes, and the homozygotes just for the red allele. So let's go back, figure that out. So that's 0.3, and that's squared. And so that's just 0.3 times 0.3, and we already figured that out. 0.09. Okay, so now one of the nice things that the Hardy-Weinberg formula does for us, or equilibrium does for us, it gives us the expectation for how many homozygotes we're going to have in that population. So this is how many homozygote dominant so we got homozygote blue, these are the heterozygotes, the proportion of the population that we expect to be heterozygous. And then we've got the proportion of the population that we expect to be homozygous, and we often talk about this as recessive. If you have a complete dominant recessive system, that's true. You won't always have a complete dominant recessive system to deal with. Okay, so that gives us some expectations for what we're going to find in the population. So if you go all the way back to the beginning where I drew out that population, guess what? I didn't identify individuals. So let's think about that. If this population is in Hardy-Weinberg equilibrium, and we saw individuals in the population like this, and be patient with my terrible drawing skills here. So check out what I've done here. We only have homozygotes in this population. That's not what we expected at all, is it? So what are we going to do here? We've got 3 over 10, we've got 30% are homozygous red, and we've got 7 over 10, 70% are homozygous blue. So let's move over to our expectations. These are the expectations. Oops. Let me move just a little bit more so you can see that better. And the reality is very different. So our observed individuals are 30% homozygous red, 0% heterozygous, and 70% homozygous blue. So we expected heterozygotes and we didn't get them. So essentially what this formula has done is it's given us an expectation if the allelic frequency is not changing. Obviously in this case we expect the allelic frequency to change, and thereby we expect that population to undergo evolution. So that's, in the simplest form, it's just a change in allelic frequency. So if we go back to that population and maybe we reconstitute it. So let's just put a line through this and let's imagine a different population. Okay, so there we go. We're not thinking about that population. What we're thinking about is a population that then has individuals that are drawn from, or that are combined in different ways. So these alleles belong to different individuals. Whoops, I need to make sure I put that blue back. All right, so maybe we can look at this population in a slightly different way. So we're going to have some of the population, and this is unavoidable in this population, that are all homozygous for blue. We might not have any that are homozygous for red, but in this case we're going to have some that are homozygous for red, and we're going to have some that are heterozygous as well. So the Hardy-Weinberg expectations are going to play out a little bit differently when we compare them in this way. So what do we have? And we can think of this either in terms of alleles, or we can think of this in terms of individuals, but we just have to be careful because we need to use one or the other when we're doing that. So I'm going to use individuals this time because it makes it a little bit simpler. So for the homozygous, we have 1, 2, 3, 4, 5. So we have 5 homozygous individuals. So 5 homozygotes. And then we have, let's see, 1, 2, 3, 4 heterozygotes. I'm going to draw that one in blue as well. And then we've got 1 homozygous red. So let's check our expectations really quickly. So our expectations were 49% were going to be homozygous blue, 42% were heterozygous, and 9% were homozygous red. That's actually really close. So we go back to here, we've only got 1 homozygous red. So we've got 1 homozygous red individual, and to get a proportion for all these, to make it a little bit, if you're following along in your head, you might have already done this, but if you're not, you might want to divide all of these by 10, because we've got 10 individuals in the population. So if we're working in alleles, then we need to divide by 20. If we're working in individuals like I just did, then we can work in 10 and divide everything by 10. So our expectation was 0.09. Our expectation was 0.42. And our expectation was 0.49. Okay? So these are the expected values. And the observed values, well, the observed values we'll do over here. So the observed for homozygote blue is 5 over 10, that's 0.5. 4 over 10 is 0.4. And 1 over 10 is 0, whoops, I want to keep that in red just so we remember what that looks like. 0.1. And how does that compare? That's pretty close, really. So we've got 50% instead of 49%, 40% instead of 42%, and 10% instead of 9%. That's really, really close. We could do some math, we could do some statistics and compare that, or in this case, we know that that's about as close as we can get. There could be a slight shift, but there's not a lot of space. We've got a small population here. That's about as close to Hardy-Weinberg expectations as we can get in this population. So I'm not going to go into the statistics to compare that today. I just want to make sure that you're thinking about how that compares to our last population. And to one more time, just say it and make sure that we're all on the same page. One of the things that we're doing when we look at the Hardy-Weinberg population, the Hardy-Weinberg expectations, is we're looking at how those alleles are distributed in individuals. In this example, where we had 70% in homozygous blue and 30% in homozygous red, there's something going on. There's something going on. Maybe heterozygotes aren't surviving, or maybe blue individuals with homozygous blue alleles prefer to mate with other individuals that are homozygous blue, and likewise for red. It's hard to tell, but there are several possibilities that make sense. One possibility that does not make sense is that there's an advantage. There's a reproductive or survival advantage for heterozygotes. That's a scenario that could not happen, or is not at least consistent with these data, because we're not seeing any heterozygotes at all. So in the case where there's a heterozygote advantage, like the genes behind sickle cell anemia, where there's an advantage in areas that have malaria, then we might have more individuals that are heterozygous than either homozygote. But we can interpret then that deviation from the expectations, from the Hardy-Weinberg expectations. So we go back over here. And it turned out that when we distributed the alleles into these individuals, we actually got a population that was in Hardy-Weinberg expectations, and we don't expect that population to change in terms of its alleles in the next generation. So I hope that that's clarified a little bit about the Hardy-Weinberg formula and Hardy-Weinberg equilibrium, and helps you to think about how you might evaluate a population. So in the beginning, the first step that we want to take is we want to look at that population, and we want to see how many alleles for each type are there. After that, we can then look at how those alleles are showing up in individuals. So that's what the Hardy-Weinberg expectation tells us. How should those alleles be distributed into individuals if the population is not changing, is not evolving? So, I hope this has helped a little bit. Have a great day.